Good morning, everyone. Brace yourself. This one's going to be a long one, okay? So the topic that we're covering today is normal approximation to the binomial distribution. Now, we're quite familiar with a binomial distribution. We know this has two outcomes. And the man who developed the formula was Bernoulli, right? We also looked at a waiting time or geometric distribution that had two outcomes. But what this is saying to us today is we're going to have a probability question that has two outcomes. But we're going to use the normal curve to approximate our answer. Now, what goes with the normal curve? Well, we know that the mean goes with the normal curve, the standard deviation goes with the normal curve, and the z-score formula goes with the normal curve. So what's really cool about it is we're in the probability unit, but we're going to revisit stuff right back from unit 2. Mean, standard dev, z-score, z-table. Okay? All right, let's take a look at our first example. It says, in a class of 25, there are 14 boys and 11 girls. We will randomly select one student every day for 20 days to read the morning prayer on the announcements, okay? A student may be selected more than once. So what you're envisioning is a bowl. And in the bowl, I would have a piece of paper for each student in my class. And each morning we'd walk in and I'd say, okay, well, I'm going to pick who's going to read the morning prayer. And the key to it is that at the end of that day, whoever read the prayer, their name's going back in the bowl. Okay, so every morning when I walk in, there'd be 25 names in the bowl. It says, what is the probability of getting exactly 10 girls? So this is a 2-outcome question, and your 2 outcomes are being selected to read the morning prayer or not selected. Those are the 2 possible outcomes, being chosen to read the morning prayer or not. Now, exactly 10 girls, this is a classic Bernoulli. How many trials? How many successes? So girls are being my success. Probability of success will be the probability of choosing a girl. So out of 25 kids, 11 to the number of successes. Probability of failure in this case would be choosing a boy to the number of failures. So 20 trials, 10 successes, 10 failures, roughly a 15% probability that out of the 20 days, 10 of them will be a girl. What is the expected number of girls? Well, we know when we're dealing with a Bernoulli, we have a quick formula for expected value. Number of trials times the probability of success. So 20 over 1 times 11 over 25 is roughly 8.8 and roughly 9 girls. So the expected number of girls, if we were running this for a month, 20 days, okay, in a month, is that 9 of those 20 days would be read by a girl. So absolutely nothing new. This is the classic Bernoulli. You did a ton of these on your assignment. Exactly is very classic Bernoulli. Expected number with 2 outcomes is our quick formula. Here's where things are going to get a little bit different. What is the probability that there will be between 8 and 15 girls? So what that means is the probability of 8 girls plus the probability of 9 girls plus the probability of 10 girls plus the probability of 11 girls plus the probability of 12 girls plus the probability of 13 girls plus the probability of 14 girls plus the probability of 15 girls. So this particular question, we understand it, but it would require 1, 2, 3, 4, 5, 6, 7, 8 iterations of the Bernoulli formula. Now, could we do it? 100%. We could calculate each probability and then add them all up and get a beautiful exact answer. But this technique obviously would take a decent amount of time. And, you know, if I changed the question and we had 55 girls or whatnot, and I said between 8 and 40, at some point doing a number of iterations of Bernoulli becomes too time consuming, and we got to come up with a bit of a better way. Okay, and that's what the goal is today. When you get to a situation where running the Bernoulli has too many iterations and it's too time consuming, what technique can we use? And the technique that we're going to use is the normal approximation. So that's the goal. We are eventually going to answer this question using our normal approximation, okay, to save ourselves some time. So let's look at, you know, a little bit of some more information before we get into how do we do it. It says the selection of students is set up as a Bernoulli trial. Selecting a girl is considered a success, and not selecting a girl or selecting a boy is considered a failure. Probability of success is 11 out of 25. Probability of failure is 14 out of 25. When we get to part C, it becomes a little bit more complicated. It'd be really time consuming to calculate from the probability of 8 all the way to probability of 15. So what we're going to do is we're going to come up with a different technique. Okay, fantastic. Let's flip. Now, let's take a look at this crazy chart. This crazy chart is a chart that Ms. Staples developed when we first did this course. God, I don't even know how many, 20 years ago. And what this chart does is she actually took the time and she ran Bernoulli 21 times and calculated the probability of a certain number of girls reading the prayer. So the probability of no girls ending up reading the prayer. The probability of 4 girls reading the prayer. The probability of 10 girls reading the prayer. The probability of 16 girls out of the 20 days reading the prayer. And the probability of 20. So what this actually is it's a probability distribution because it's all of the possible outcomes. Okay. And it's their associated probability. So that's what she did. She took the time and she did that for us. All of the possible outcomes of reading of girls reading the morning prayer. Okay, now if we could take a moment, do me a favor and take a look at these probabilities. Let's look at them together. Super small, 2%, 4%, 8%, 13%, 17%, 18%, 15%, 11, 6, 3, 1, small, small, small. So what you're seeing when you're looking at these probabilities is super, super small, reaching a peak, dropping, and then super small. So the probabilities resemble a normal distribution. A bell curve. Okay, so that's okay. We've seen that before. And now what we're going to do is we're going to just take a little bit of time to graph it, okay? And I don't want you worrying. I don't want you thinking, oh my God, I'm going to have to get into graphing again. No, this is a one-shot deal just for our notes, just for the sake of teaching purposes. Along the bottom, we're going to put number of successes. And that's the number of girls reading prayer. And we're going to start at 0 and we're going to go all the way to 20 because we were reading the prayer for 20 days. Along the y-axis, we're going to go probability. And that's going to be in percent. And we're going to start at 0 and go up in increments of 2 because my largest percentage, I think, was around 18%. Beautiful. Okay. So let's take a moment, and I'm going to start in the middle just because I find it easier. So at 9 girls reading the prayer, which was our expected number, we're at roughly 18%, just below. At 10, we're at roughly 15. At 11, we're at roughly 11. At 12, we're at roughly 6. At 13, we're at roughly 3. At 14, we're at roughly 1. And all these little tail ones over here, I'm just going to call them super small. And I'm just going to connect those dots in a nice fluid motion. Okay? I'm going to do the same thing for 8. 8 was at about 17. 7 was at about 13. 6 was at about 8. 5 was at about 4. 4 was at about 2, just under 2. And 3, 2, 1, and 0 were super duper small. And I'm going to connect those in a fluid motion. So now it's very clear that you're noticing the mound shape, the bell curve, and that this is really representing a normal distribution. And because it is, maybe we can use our new title, Normal Approximation. That sounds kind of nice. Okay, let's put just a little pink line to indicating the peak of the curve, if you don't mind. Okay. All right. Let's flip when you're ready. I know doing the graph, you might have to stop the video and kind of get your graph finished, and that's okay. And again, please don't worry, you won't be graphing on your test. Okay. So what do we need when we're working with a normal curve? Well, we kind of talked about this already. With a normal curve, you need your x-bar, which is your mean. You need your sigma, which is your standard dev. And you need your z-score. Okay. Well, guess what? The mean is our expected value. And we have a formula for expected value, NP. And our standard deviation, the formula is the square root of N times P times Q. Okay, so let's take a look at this. Our mean is going to be the number of trials times the probability of success. I think we already calculated this on the front page. It was approximately 8.8. Okay. Our standard dev is the square root of the number of trials times the probability of success times the probability of failure. Now, with this particular calculation, I would definitely ask for you to get your calculator out and try it, because a lot of calculators are fussy with this square root. Some of you will be able to type in exactly the way you're seeing it written on the paper. Some of you will have to do your multiplication first and then square root it. So it would be a nice idea if you took the time right now and just played around with that. So 20 times 11 over 25 times 14 over 25 square rooted is 2.22. So we've got a mean of 8.8, or an expected value of roughly 8.8 or 9, and we've got a standard dev of 2.2. Now, here's where I need you to kind of listen to me, because this gets kind of weird. These approximations are, sorry, that's a typo on my part, are considered to be reasonable if P is fairly close to 5, or 0.5, that's our probability of success, and N is fairly large. To test this, we use a rule. NP must be greater than 5, and NQ must be greater than 5. Okay, so what does that mean in simple English? That means that if you get a question where the question is requiring you to do a ton of iterations of Bernoulli, and you're thinking, I don't want to go through all this work, I'm going to try my normal approximation. The very, very, very first step, is to run what we call the test. The test is looking to see whether your probability of success is close to 0.5 and your N is fairly large. Now, that's very obscure. What do you mean N is fairly large? I don't know. N is 20. Is that large enough? Is 20 large enough? Is it too small? I don't know. So the test says take your N, multiply it by your P, take your N, multiply it by your Q. When I take my N and I multiply it by my P, I get 8.8. And when I take my N and I multiply it by my Q, I get 11.2. Both of these are greater than 5. As long as both of them are greater than 5, your NP and your NQ, as long as both of them are greater than 5, this technique of approximation is a go for you. Okay? If you happen to get NP being less than 5, but NQ being greater, this technique is a no-go, and you have to do it the long way. Same thing. If NP was greater than 5 and NQ wasn't, this technique would be a no-go, and you would have to do it the long way. Okay? Keywords, both have to be greater than 5. So if you can't pass the test, then you have to do it the long way. Okay, so we've completed step 1. Now we're going to do step 2. Step 2 says, once you've passed the test, calculate your mean and calculate your standard dev. Okay, we're good to go. So you're thinking, okay, we passed the test. Both are greater than 5. We calculated our mean. We calculated our standard dev. What's next? Okay, here comes the next part that I need you listening to me. we got one more issue. You know, in math, there's always one more issue. That's the way it works. The data that is graphed is discrete. So let's have a little review of discrete. Discrete data is whole number data, okay? And this is actually whole number countable data, the number of girls that are going to be reading the prayer. 9 girls, 12 girls, 3 girls, discrete data. Okay, let's read that again. The data that's graphed is discrete. The number of successes, the number of girls that are reading the morning prayer. However, a normal curve can only be fit to continuous data. Continuous data is decimally data. Oh no, what do we do? Okay, and this is where things get kind of complicated. Let's read and then we'll go back to our picture, okay? It says we need to treat each possible outcome as an interval. For example, 8 successes or 8 girls reading the morning prayer would be considered anything between 7.5 and 8.5. This way, when you're considering any values for the normal distribution, we would round to 8. So you know that if I gave you a number like 7.5, you would round to 8. 7.6, 7.7, 7.8, 7.9, 8, 8.1, 8.2, 8.3, 8.4, all rounds to 8. We extend the unit from 7.5 to 8.5. I know 8.5 doesn't round to 8. I know there's people out there arguing with me. That's okay. We usually have a discussion. But we keep the interval so that it has continuity, 7.5 to 8.5. So hold on. Let's go back to our graph and adjust with some bars. Okay, so if everybody can pull out their graph, and you're going to need to bear with me here for a second, okay? You're just going to have to trust me and bear with me. I'm going to get a red pen. And what I'm going to tell you is that 9 girls really is the interval between 8.5 and 9.5. 10 girls is the interval between 9.5 and 10.5. 11 girls is between 10.5 and 11.5. 11 or 12 girls is between 11.5 and 12.5. Same on the other side. This would continue, okay? Same on the other side. 8 girls is between 7.5 and 8.5. 7 girls is between 6.5 and 7.5. 6 girls is between 5.5 and 6.5. 5 girls is between 4.5 and 5.5. So what I'm saying to you, and I'm just going to continue my bars as I'm talking, is that because the data that we're dealing with is discrete, yet the normal curve only can work with continuous data, we have to morph the discrete data that we're working with so it fits into a continuous model. And the way we morph it, the way we alter it slightly, is that we look at each discrete value as an interval. So 9 girls would really be 8.5 to 9.5. 14 girls would really be 13.5 to 14.5. And the reason being is that the numbers in that interval, in general, okay, will round to the discrete value. The numbers in this interval round to 9. The numbers in this interval, in general, round to 14. The numbers in this interval, in general, round to 4. Okay, so we're bringing the two techniques together and we have to kind of morph the data a little bit to meet the requirements. Now, is this going to be important for you per se for a test, this picture and whatnot? No, this is all the theory behind it, okay? You're not going to be graphing, you're not going to be answering what interval, none of that stuff, okay? This is just the theory behind it. So how about we go back to the example and we actually finally get to answering it, because that's the problem with this lesson. There's a lot of theory and we spend a lot of time talking and we don't even get to answering the question until almost the very end. So step one is the test. N, P, yep, and Q. Yep, passed. Mean, standard dev. So done, done. Now we're finally at step 3.